Thank you very much. I hope can you hear me at the back? That's good. So we'll talk about the universe and the cosmology, cosmological problems we can solve with hydrogen 21 centimeter line. It's a kind of research talk, so I decided to talk about my own research. That's what I actively do, and I'll show you some of the results. It's a very hot topic nowadays in cosmology. And if you don't understand something, please just interrupt me, raise your hand, and I'm happy to go slower or to explain slides or results better. So please do interrupt me. I don't know how to. We didn't check. Okay. So I'll give you first a background of what kind of phenomena we can study in principle, and hydrogen is one of the easiest elements to form. It's the simplest structure, so one proton, one electron, and it was created in abundance during Big Bang nucleosynthesis. So in the first moments of the existence of our universe, most of the material that was formed was in the form of hydrogen. Of course, it was not combined in neutral atoms at the beginning because the energy of the universe was too hot. So there was plasma, basically, protons and electrons were separated. And this plasma interacted also with radiation. I understand you had many talks on CMB, so probably most of you know this phenomenon called cosmic microwave background radiation. So in this map that shows the evolution history of the universe, it's on the very left. And CMB is relic radiation from the Big Bang. So when the universe expanded enough and cooled down enough for these neutral atoms to combine, so we got a lot of neutral hydrogen, but also cosmic microwave background radiation decoupled from this plasma. So plasma combined and cosmic microwave background decoupled. It's shown as fluctuations here. So there are red and yellow dots that show regions in the CMB which are a bit hotter than the mean, and blue regions are those that are a bit colder. So same fluctuations were actually imprinted in the distribution of hydrogen and all other matter when photons recombined. So by studying CMB, and that's not the topic of my talk, but I just want to kind of bring you all to the same page. But looking at the CMB maps, we see also the map of how matter was distributed at the very, very early stages in the evolution of the universe. So the matter was distributed non-uniformly. There were regions where there was a bit more material and a bit less material. And of course, due to gravity, these regions that contain more matter were collapsing, forming a large-scale structure, what we call also a cosmic web. So combined, there were regions where there was more dark matter and also baryonic matter, and regions that were called voids that were nearly devoid of material. After CMB decoupled, so at this very early stages, the universe basically was dark and cold. It was expanding, and the more volume expands, the cooler is the gas. That's one of the basic thermodynamical properties. And so the universe was expanding, gas was cooling down, the CMB was also cooling down, and there was nothing. There were only these very small scale fluctuations, so very low amplitude fluctuations that slowly grew to form large scale structure. So this period between CMB, shortly after the CMB decoupling, is called dark ages because there was nothing. However, this matter collapses, and then suddenly, so slowly, not suddenly, but dark matter halos form. So these are the first bound structures in the universe, and they are mostly composed of dark matter, and they become heavy enough to attract gas. So gas has extra thermodynamic properties. It has pressure, and so it's harder to collapse it and form bound objects such as stars compared to dark matter, right? Dark matter structures grow even before CMB decoupling. So, but as soon as we have massive enough dark matter clumps, around 10 to the 6 solar masses, they are strong enough to attract gas, and this gas collapses inside dark matter halos, and then through collapse, actually, so it falls down, heats up, emits photons that carry all this excess energy away, and that's how it cools down. Actually, it's called radiative cooling. So it cools down enough to form stars. And so bright dots here you see are the first star-forming regions in the universe, and it happened not long ago, so not long after this CMB decoupling. Sometimes stars are said to form 60 million years after the Big Bang, depending on the theory you're doing. So this epoch when the first stars form, we now refer to it as cosmic dawn, a bit poetic, but that's the dawn of star formation in the universe. Before that, there were no stars at all. So at some moment, the universe makes this transition from completely dark and cold universe to the place where there is suddenly starlight. And so the starlight illuminates the whole background. So the space filled mostly with neutral hydrogen. And of course, the starlight has feedback on the gas. So what stars can do, they radiate the gas around, and this radiation can reheat the gas. So these bubbles around star-forming regions, I'm not sure this works. So these grayish bubbles are actually bubbles of hot and ionized gas, because stars emit UV radiation that also ionizes neutral gas. But also stars, they live and die, and in the process of their cycle, some stars create black holes, so also first black holes in the history of the universe. And if there are specific conditions, so if stars form in pairs or triplets, and one of them ends up as a compact object, such as a black hole or neutron star, they can create what is called X-ray binaries. And so such X-ray binaries would produce a lot of X-rays, which would also heat up the gas. So you can imagine around every gray bubble that is ionized region, there are also bubbles of hot gas, but X-rays can travel much further than UV photons. So each star-forming region would heat up quite a big chunk of the universe around it. Okay, and as the universe evolves, there are more and more dark matter halos that form more and more stars, and slowly this dark matter halos and galaxies, first galaxies within them, grow and ionize and heat up more and more gas. So at some point we arrive to this epoch when all gas is hot and ionized, and we call it the epoch of reionization. So this whole process takes around 1 billion years out of 13.7 billion years that the universe evolved. So today we are here on the right-hand side somewhere, and the universe is 13.7 years old. And all the intergalactic gas is actually hot and ionized. There is no neutral hydrogen left. So after this end of the epoch of reionization, the universe spans around 13 billion years in this hot and ionized state, when all galaxies are in their mature, kind of evolved state. And that's what we see today with telescopes such as JWST, so James Webb Space Telescope. So that's in a nutshell the evolution history of the universe. And out of it, we haven't observed much. So we have observed, of course, the CMB edges. CMB kind of map was created or observed by many satellites and many ground telescopes such as COBE, WMAP, Planck, ACT, SPT, and so on. So this era is well studied, and we know our cosmological model pretty well just by looking at the universe when it was very young. And then, of course, there are observations of this more evolved stage of the universe when the surveys such as with Bose, DESI, and others have mapped large chunks of the universe around us. So we know pretty well what is the structure of the universe, what are the statistical properties of the cosmic web. And we have studied many galaxies in great details, and also our own galaxy, of course. But as we push to further into this epochs of dark ages and first star formation, there are literally no observations yet of this epoch. There are some upper limits that I will be talking about today, but there are no detections that can inform us on how the universe actually looked like. So what I do in my research is to build models of this evolution of the universe and play with the parameters of star formation and black hole binary formation, and then try to constrain these models with existing observations. So I'll be showing you today some results. And again, if it's a bit too technical, please feel free to interrupt me and ask questions. So of course, I don't know if you had talks on JWST. We have a big group here at Cambridge that is actually doing science with James Webb Space Telescope. And one of the kind of, to me, most interesting science cases of JWST is to study galaxies deep into this epoch of reionization. So JWST is a very sensitive telescope that can see galaxies as early as 0.3 gigayears after the Big Bang, so at redshift 13. And this would be galaxies roughly at this epoch when it's not the very first galaxies, but it's also way far from us. So these are one of the earliest galaxies we have ever seen. And so these are the brightest galaxies at that epoch because JWST has also finite sensitivity and it can only see the brightest monstrous beings at this kind of beginning of the epoch of reionization. So JWST appears to see many of these bright galaxies, which is one of the mysteries today. I'm not trying to explain it here, but it also doesn't see the majority of galaxies that exist here that are likely below its sensitivity limit. Right, so there is a big population of galaxies, like an iceberg structure. JWST sees the very tip of it, but the majority of galaxies are still below the resolution limit and sensitivity limit. So there are many of the small galaxies formed in small dark matter halos that have impact on the universe. So they heat and ionize the gas here. They have impact on the neutral hydrogen in the intergalactic medium, but they are well below sensitivity of JWST. And so we still, even with detections from JWST, we have this portion of the universe that includes dark ages and the formation of first stars and black holes that are not observed at all by existing telescopes. Right, so these epochs are, as I said, characterized by this empty expanding universe that is cold, mostly neutral, formation of first stars and black holes in small halos, and gradual impact of the stars on the intergalactic medium, so they heat and reionize the gas. So it turns out that neutral hydrogen, so it's the most abundant and simple structure in the universe, can actually help us to probe this epoch. So all this of the space between the gray bubbles, symbolically here, is full of neutral hydrogen, and that's the most abundant element. And this neutral hydrogen, it creates, of course, energy levels of the atom, and it emits and absorbs photons all the time. So one of the transitions of hydrogen is called the hyperfine splitting transition. It's due to interactions between spins of proton and electron, and it's a forbidden transition, so it doesn't happen in the lab. It takes 10 to the 15 years to create this photon of 21 centimeter from this transition in a lab, so we cannot observe it here on Earth. But it turns out that the universe is so vast, the space and the amount of this hydrogen is so great that we get enough of these photons, or we predict to have enough of them from this cosmic history to be observable. And that's what 21 centimeter cosmology is about. It's about detecting this very rare but numerous in terms of cosmic volume photons that are created by these hydrogen atoms. And to see the signal from these epochs of cosmic dawn and dark ages, and to try to interpret it in terms of star formation and cosmology. And nowadays there are many telescopes, they're all in radio, so 21 centimeter wavelength corresponds to 1.4 gigahertz, it's in radio band. And also because the universe expands from the moment they were created, sometimes by a factor of 100, this wavelength is expanded as well. So we're now trying to detect photons of frequencies between 100 megahertz to 200, so between, say, 50 and 200 megahertz today that correspond to these epochs. Well, it turns out that there are many telescopes that are doing that, and on the top row you see some examples. So this is an antenna in India placed on a lake to avoid reflections from the ground. It's called Saras, and this is their third version. They actually, if you visit their lab, they have the whole evolution history of the antenna from a tabletop to a spherical antenna to this conical now. And then in the middle, this is a square kilometer array. So that's one of the biggest radio telescopes. It's now being designed and built actually in South Africa and Australia. And this is antennas that actually are built to look deep into the universe and try to see the signal from dark ages and cosmic dawn. And on the right, you see an antenna that is actually designed and built here in Cambridge with a group at Babcock Center. So they are designing radio instrumentation also for the square kilometer array. And this antenna is already in the desert in South Africa taking data now. So all these experiments are trying to see the epoch of first star formation so I'll show you what they're trying to measure. So because the Earth is kind of enveloped in ionosphere, the outer layer is ionized and detects as a mirror to very low frequencies in radio band. And so if you're trying to observe this epoch, so of dark ages, the hydrogen waves are actually so big that they will bounce off ionosphere. These are very low radio frequencies, below 50 megahertz or 30 megahertz, depending where you are. And so this epoch is only accessible from the moon. And nowadays there are many telescopes and many groups in the world, so many groups, sorry, not telescopes, that are trying to design satellites and lunar experiments with a science goal in mind to detect 21 centimeter signal from dark ages. All this era of first star formation and epoch of reionization are accessible from the ground, and as I said, there are many telescopes that are already taking data. So the advantage of 21 centimeter line as opposed to CMB, for example, so CMB actually measures very thin two-dimensional sphere when photons decoupled, and it happened at the same time around the whole universe when conditions were right. So it's actually a two-dimensional snapshot of the universe at specific time. As opposed to that, 21 centimeter will be a three-dimensional scan of the whole universe. So it's like taking a tomographic scan. And from every point in time, we will have information about that state of the universe at a specific radio wavelength because of the expansion of the universe. So the created signal is at 21 centimeter, more or less exactly, I think 21.1. And so from every instant in time, it is at 21 centimeter originally, but then every point in time suffers a different expansion. So waves are expanded by a different factor until they reach us. And so by observing different radio frequencies, we would get information from different stages in cosmic history. Right, so on this transition from cosmic observations to ground-based observations is roughly at 50 megahertz. Unfortunately, 100 megahertz that probes something here falls within FM band, so it's highly contaminated by radio emission on Earth. And it would also benefit to go to space to avoid this contamination. It's called radio frequency interference. So let's now try to understand what are the physical properties that the signal can actually teach us about. So first of all, it's a neutral hydrogen signal, and it's only produced by hydrogen atoms, so proton and electron combined in the ground state. So every time we have neutral hydrogen in the universe, we can detect the signal in principle. And so the universe was fully ionized before the CMB decoupling. There was no signal then, but then it recombined. So most of the gas was in neutral state. So we have a pretty high fraction of neutral hydrogen. But then as the stars and galaxies start reionizing the gas, neutral fraction drops. So this purple line shows neutral fraction, roughly, as it evolves with cosmic time. So today there is no signal from the intergalactic medium just because all of it is ionized, as I mentioned before. So to the leading order, the signal, which I will refer to as brightness temperature, is measured in terms of brightness temperature. It's another measure of intensity of the radio signal. But to the leading order, it's just proportional to the amount of neutral hydrogen. So to this proportional to the neutral fraction. To the next order, there is a correction from radiative transfer equation. So one can solve how radiation propagates. And we observe actually the signal with a background radiation that is the CMB. So it's actually, we can imagine a cloud of neutral hydrogen atoms. And then there is a CMB radiation that goes through it. So CMB has a spectrum of black body. It's composed of different wavelengths. And so hydrogen atoms can absorb 21 centimeter transition photons from it. It's like spectral distortions that you heard from Jens, but that's an aspect of it. So it creates an absorption from the CMB if the gas is actually colder. But if the gas is hotter, it will emit at the same frequency and will create a bump in the CMB. So all predictions that I will be showing to you are after we subtract the CMB intensity, and they're just residual. So this factor tells you roughly in comparison to the background radiation of the CMB or anything else that exists at that frequency, if the gas is colder or hotter, it will imprint the signal. So we will have information in this brightness temperature that we observed. Right, so it's just thermodynamics. If gas is colder, it will absorb, trying to get to the equilibrium with the CMB. If gas is hotter, it will emit. So if gas is much hotter than the CMB, this term is smaller than 1, so we will see a signal, what is called an emission of 21 centimeter. If gas is colder, this term will be larger than unity. And we will see the signal in absorption, so negative kind of signal. So this plot here, the green line shows how gas temperature, CMB temperature cools down as the universe expands. Gas and also radiation cool down because of the expansion. So, but the expansion rate due to thermodynamical properties is different in gas and photons. Gas cools down faster, so this yellow line shows how gas cools down. Most of thermal history of the universe, the gas is colder than the radiation. So we would see 21 centimeter in absorption. But then because X-ray binaries form and heat up the gas, the temperature of the gas will rise up above the CMB and we would see signal emission. Of course, we need gas to be neutral to see this information. But in principle, from observing 21 centimeter signal, we can already know when X-ray binaries formed and heated up the gas above the CMB. So we can learn about properties of the first ever black holes. Okay, so this is nice and easy, but it comes out of a complicated radiative transfer equation that one needs to solve. And also this is true only in the presence of stars, actually. So that's another important property. So this term appears here, only starlight, we say couples, so drives the characteristic temperature of this 21 centimeter transition, and then couples it to the temperature of how gas is hot or cold, to the temperature of the gas. Without stars, this actually term would tend to 1, so everything would be in the equilibrium with the CMB, background radiation, so we would not be able to observe anything. So it's just due to the first ever, so sorry, I should have put that somewhere here, when the first stars formed, we start getting this coupling, and we see the signal from 21 centimeter neutral hydrogen in absorption or emission as opposed to radiative background. This is clear because it's an important point. Okay, good. Okay, so just from this simple picture, we already see that we can learn about first star formation. So when first stars formed, we start seeing signal. We see how gas is colder or hotter than the CMB. We can read of star formation rate and the rate of formation of X-ray binaries. And we can also see when gas transitions from neutral to ionized state. The rate of this cooling of the gas and radiation depend also on the cosmological content. So how what cosmological model actually is implemented in the universe. Of course, we know that from the CMB, but we want also to test it over the whole redshift range or time range that we have here. And of course, if there are any weird phenomena, say dark matter, the universe is full of dark matter, and if it's dark matter annihilates or decays, or if it has weird quantum properties, that would also be manifested in the deviations of this line. So say if dark matter interacts with gas so that gas cools down faster than shown here, we would see 21 centimeter signal to be much deeper. That's not the end of the story. Like in the CMB, you see all fluctuations in the CMB, as we call them. So these regions that are hotter or colder, depending on where the matter is more concentrated or less concentrated. So we see similar fluctuations in the 21 centimeter signal, and there are many sources of them, actually. So every term in this equation, and that's not a complete story, there are more terms that are second and third order, but every one of these terms actually fluctuates around the sky. So for example, neutral fraction also follows fluctuations in the CMB, because regions where there is more matter, there will be more neutral gas. So overall abundance of hydrogen atoms is higher, and the signal will be boosted by that. So gas temperature also depends on we said that in the absence of stars, gas is cold. In the presence of stars, gas is hot, but it's actually non-uniform around the universe. So stars are distributed non-uniformly. There are some overdense regions where stars form first. And these regions will be hotter because first stars will heat up the gas sooner, while the regions like here, where there are no stars until later on, will remain cold. And so we will see fluctuation in 21 centimeter signal, depending if the gas is hot or cold. And then we also have fluctuations in line background, so this coupling from stars. and any other source that affects the signal will imprint fluctuations. So overall, you start seeing the picture. It's a very rich picture. There is evolution in time. There is a difference, so fluctuation pattern, so different signal on different scales. And overall, we can learn a lot from observing the signal over cosmic time. So this actually is a simulation that I wrote as a PhD student, and I keep working on that. And now my students work on it. And this is a snapshot that one of my students, Jiten Khanha, created. And it shows the evolution in this 21 centimeter signal across redshift or time or frequency. So as I said, the frequency corresponds to cosmic time. And in a simulation box that is almost 1.5 gigaparsecs large, so a huge cosmic volume. We see that there is evolution in overall magnitude of the signal. So this is brightness temperature, we measure it in millikelvins, and that's after we subtract the CMB. So this shows overall signal, and the fluctuations in it because there is change in cosmic properties depending on the location. So that's what we expect to observe finally when there is enough data. But it also, there are many assumptions that went into this modeling. So there is a prescription for star formation cosmology, in which dark matter halo stars form, which halos form X-ray binaries and which not, and how efficient the stars are in creating Lyman alpha photons, ionizing the gas, heating up the gas. So what we do now is actually run the simulation 10,000 times on high performance computing here at Cambridge, create such snapshots or such pictures for different cosmological and astrophysical assumptions, and then try to see which models fit better data that already exists. We also use machine learning methods to actually, 10,000 is not good enough actually, when you try fitting data to observations or other way, theory to observations. So we use machine learning methods to create more probes of astrophysical parameters. Okay, so now we are working with many telescopes. There are many existing telescopes, and many of them already have upper limits. There is only one detection that is not confirmed. So we are only dealing with upper limits, and an upper limit is not a measurement, it's just a kind of information bound for signals that are not present. So there is some level of signal that can still be hidden in noises of the telescope or below the sensitivity of the telescope. If signals are higher than some sensitivity limit, they would have been detected, but they haven't been, so we can rule them out. And so there is data from all this, the two telescopes on the left that are called global signal experiments that have very broad radio beam, so they have beam this big literally, and they average information within the beam. And what they have is just a kind of average spectrum of 21 centimeter that tell us information about the cosmic clock, basically, when in average in the universe first stars form, when in average X-ray binaries happen. Both of the telescopes have interesting data that I will show you later what we learned from it. Another class of telescopes are called interferometers, and these are basically arrays of radio antenna. So, for example, square kilometer array is being designed. That's a snapshot picture in Australia. But there is also Hera that is composed of huge dishes that are sensitive to radio waves. There is Nanufar in France and Blofar in Netherlands. MWA was also in Australia and LIDA in the US. So these telescopes that we have also, in addition to just measuring total signal, they have spatial resolution. because Raman antennas, and they can give us information about fluctuations in the signal and eventually fluctuations of a redshift range. So they can actually eventually give us the whole map. By design, different telescopes are sensitive to specific radio frequencies, of course, but most of them have very broad radio frequency ranges. So this one was actually the first ever detection claimed in the history of 21 centimeter signal from cosmic dawn, done with this. I don't know if you heard already about this edges signal. Have you? No, that's one of the another big kind of mysteries, but probably it's just systematic error of the telescope. So this first ever detection was announced in 2019, so pre-pandemic, made with this small antenna in Australia that is called EDGES experiment. And they very carefully took data and refined their instrumentation for 10 years or more, even first in the basement of the institute in Arizona. And then they built good enough experiment to put it in Australia. They rotated it many times. They made a copy of it, put it somewhere else in Oregon. And they keep reporting this shape of the signal after they also subtract so for radio frequency interference, and also our galaxy creates radio noises, so that all needs to be carefully subtracted. But at the end, they inevitably report this signal shape, and this is an absorption. So if it's cosmological, it means that the gas at those frequencies that they report here, around 200, no, that's cosmic time. So this corresponds to 78 megahertz. So they see this deep absorption, which would correspond to a very cold gas at redshift 18, so 78 megahertz frequency, that would correspond to formation of the very first stars. So that was a huge kind of boom in our field, a lot of excitement, and for already 5 years, people are trying to understand if it's real or not. So if you put it in the context of normal astrophysical scenarios that I just told you about, so if you assume dark matter collapse in small halos from stars first, they reheat and reionize the gas, and gas cooled down due to expansion of the universe. You vary all possible astrophysical properties of stars, so how big dark matter halos are, how efficient gas falls in, how efficient stars form, how efficient are they in ionizing and heating, so taking all these efficiencies from 0 to 1. So these are the absolute limits. You end up with this gray sample of models. So these are the whole, our understanding of potential evolution of the universe. And if you put edges signal on top, it's this red line, so it's clearly an outlier. It doesn't fit within this normal understanding that we have. And our normal understanding is also consistent with the CMB and with large scale structure. So it all is nice and well in theory, but the observation doesn't agree. So it's been very exciting 5 years trying to understand if the signal is cosmological or not. And it looks like it's probably not, it's just a systematic, but there is no other observations that we have that could probe signal from that era. So actually this tiny Saras antenna tried to confirm or reject the signal, and then made an observation in nearly the same frequency range. So it doesn't correspond completely. This is the edges signal, and the gray band is the band in which Saras took data. So it's not completely the same, but they don't see the signal. So in just a year ago, basically, they published that they haven't seen the signal yet. And it's a 95.3% disagreement with edges. So this is one of the biggest kind of excitements that happened recently in this field. Other than that, we have upper limits. So this is an example of HERA experiment. That's the most sensitive interferometer that exists nowadays. And these green points and black circles and white circles are the data from the HERA telescope. And all these colorful lines are the models that we predict that might be realized in nature. Right, and so HERA has already power to reject some of the signals, which means it probes this astrophysical parameter space to some degree, but most of these models are still consistent with HERA data. And HERA only actually observes in a very narrow frequency range at the moment, focusing on this pretty low redshifts, 8 and 10. So it does not measure anything in this epoch, but they're actually building nowadays instrumentation to be sensitive also to this. And there is also data taken from this part of the sky, but it's not been analyzed yet. So it was actually enabled by the development done here in Cambridge. They built receivers for this antenna to be able to detect signals from cosmic dawn. Okay, so are there any questions so far? No, okay, so keep talking about what can we learn actually in terms of astrophysics and show some of the real scientific results. So as I said, the signal is sensitive to the processes of reionization, heating, and star formation. And we can try to probe properties of the very first stars actually that have ever been formed in the universe using the simple hydrogen atoms. So it turns out that we don't know much about first stars. We know that in the beginning, of course, there was from the CMB, we know that there were no stars. It's all tiny fluctuations. And we know that today the universe is full of stars and big massive galaxies. But we don't know very well how this transition happened. And if you ask people who do high resolution numerical simulations of formation of these first stars, they don't very much agree in between themselves. So this upper panel shows the distribution of masses of first stars. So on horizontal axis are stellar masses from 1/100th of solar mass to 1,000 of solar mass, so huge stars. And in y-axis, on vertical axis, you see the distribution. So what is the fraction of all stellar mass at early times in specific mass range? And we see that different colors show different simulation results of this first star formation. We see that they are all over the place here. There are some simulations with red and yellow that show that stars can be as massive as 100 and 1,000 solar masses. And in these cases, there are no light stars at all at early times. Of course, now we have a lot of them, but they can form now because chemical properties of the gas are very different to what we had at early times. So early on, when we had hydrogen and helium, and these elements, in order to form a star from them, they don't cool down very much, so they would form big objects and up to 1,000 solar masses. While today we have metally enriched gas, and this gas can actually collapse to much smaller objects and form much lighter stars like our sun. But anyway, some simulations predict that even at early times with this hydrogen and helium, one could get stars as light as 1/10 of the star of the sun. So this is theory, right? Simulations, the state-of-the-art numerical simulations, the best we can do. And actually observations with neutral hydrogen, 21 centimeter line, can actually tell us which one of these simulations are correct. Of course, it's a very difficult observation. The signal is still very weak. It's it hasn't been observed except for the edges detection. And there are many noises added up. So it will take a while until we will be able to distinguish between these curves. But there is the potential in there. And this work has been done by Thomas Gacy-Jones. Some of you know him. So he's my PhD student at Cavendish, actually. So what he did was to model the spectra of these first stars depending on their masses and mass distribution. And he greatly improved the code that we had before. So before, we modeled spectrum as this orange line. So this is just black body. We model stars as a black body radiation. But in reality, they have emission and absorption lines. And so this blue line is what you get if you do a more careful modeling of stellar atmospheres. And then Thomas looked at different, we call them initial mass functions. So this distribution of stellar mass and contribution. So just a probability distribution of masses, how many mass there is in every at every point as opposed to stellar mass. And then depending on what theory you assume, you would get different emissivities of the stars. And I hope I showed you that this emissivity, how many photons each star emits in various frequency bands, can affect 21 centimeter signal. So this plot shows that stellar masses, so depending on what we assume for stellar masses, we would get different emissivity. And this means we will have the signatures in the 21 centimeter signal. So this was the first study that we did almost 1.5 years ago. And here we only focused on this Lyman alpha coupling. So how gas is coupled to the 21 centimeter brightness temperature. And it looks like that if we only take into account this effect, we can read off stellar mass. So this color code shows mass of the stars. So here in this first study, we assume that all masses were the same. So if stars were all very light, the signals will have will change as a function of stellar mass, both global signals, so the sky average, and the power spectrum in fluctuations. But if we take very massive halos, stars in yellow, so all stars, if all stars were as massive as 100 solar masses, we don't have this information anymore in 21 centimeter signal because they all will produce similar emissivities. So this is just one effect, and now Thomas is working on adding more effects, such as what X-ray binary population comes out of each one of these assumptions. And there is way more sensitivity, so we create even stronger signatures at later times from this X-ray heating properties. So that's still work in preparation. Next process that we can hope to constrain is this first supernovae, basically. So stars live their lifetime, and massive stars burn out very quickly. And if it's a 100 solar mass star, it will explode as a supernova in a few million years. So very quickly after first stars form, they explode as supernovae. And what supernova does is create heavier metals. It also expels all gas from this tiny, small dark matter halos. So dark matter halos stop forming stars for some time until gas recollapses. And it's enriched by metals, so it forms next population of stars that have different properties to the very first stars. And here we showed that actually signals will be sensitive to this transition between first stars, which are called population 3 for some reason, to the next generation of population 2 stars. So this is just an example of how the speed of this recollapse would affect global 21 centimeter signal. So just the takeaway message, there are different curves at different colors. So in principle, we can learn this information from the signal. They're not all aligned one on top of the other. Okay, so this stars, and then as I said, they some explode the supernovae, others will collapse and form black holes. And these black holes, if they're in binaries, they can heat up the gas. And the character of the heating processes will also be imprinted in 21 centimeter signal, and then we can read it off and interpret in terms of so understand what properties first X-ray sources had during the first billion years. Okay, so this is a bit technical. This shows fluctuations in 21 centimeter signal as a function of time on the horizontal axis and also spatial scale on the vertical axis. So this is kind of 2D information that we can learn, so both scales and time using interferometers such as Hera or the SK. And this shows the difference in this 2D power spectrum for different X-ray properties. So here I show you a result of realistic black hole binary spectrum, this kind of a model with a peak. So that's what the population of realistic first X-ray binaries would produce in terms of X-ray intensity. It's a function of frequency that they produce, and it has a peak. So most of radiation from this X-ray binaries comes out at 1 q-electron volt. And as of, if you compare that to another theory where most sources create very low energy photons, the signature in the 21 centimeter background would be very different. So in principle, we can distinguish spectral properties of first sources in X-ray by observing the signal. And this is important because we can learn about properties of first black hole binaries, again, how massive they were, and if it was black hole binary population that heated up the gas or something else. So for example, this power law spectrum would correspond to another type of heating sources. And so this ability to distinguish these heating sources actually depends on the frequency of photons. So if they're very energetic, they will travel far away from sources and inject their energy further away from a star forming region. While if they're very low energy, they will inject most of their energy right away, so creating very strong small scale fluctuations in 21 centimeter signal. I'll skip some things because I think my time is almost up. So another potential heating source are cosmic rays. And again, Thomas, under my supervision, showed that cosmic rays, so these are charged particles, they would have a very different heating profile compared to X-rays. So by observing this 21 centimeter maps, on top you have cosmic rays, and on the bottom you have, so on the right, so left is cosmic rays, right is X-ray binaries. So these two sources of X-rays or heating would imprint very different information. Okay, just want to show you what we learned today from Hera observations and others. So existing observations, as I said, are not detections except for this edges data. Otherwise, we have upper limits. But these upper limits are already interesting enough to start ruling out signals. And this is work done by another of my PhD students. So he's now a postdoc, Harry Bevins. So we looked at the very large range of models in this blue. So these are all possibilities of 21 centimeter signals, and this shows a very deep absorption profile. It's covered, so he did statistical analysis. So in blue, we show what is called prior distribution of theoretical models, all the possible range of models that we can think about. And then in red and green are the posterior, so models that are compatible with observations so far. So red are compatible with this Saros-3 antenna that observes very early times, and green are compatible with Saros-2 that observes later epochs. So we see that both red and green are different from blue, and it means that there is information that we already now learn from these experiments about very early times. So these are ratios 20, which correspond to the just 500 million year in cosmic history. Just to end here, another work in preparation is where we try to see if current data can actually tell us something about these very first stars. And here we show star formation efficiency in population 2, so chemically enriched stars versus population 3 stars. And there is, again, there is kind of slopes in these probabilities, so we can learn something. And I'll stop here. And if you are curious, you can ask me about more details offline. So thank you.
Questions, audience?
It cannot be all clear because it's not clear to me also, so yes.
Could you please go back to your slide with the simulation result with the color plot, the one with the temperatures?
I think I know what you mean.
Yes.
Yeah, that one.
So, first of all, I don't quite understand what the megaparsecs axis represents. What kind of distance?
Right. So in cosmology, we measure everything in megaparsec or gigaparsec. I don't remember off the top of my head how many centimeters.
Oh, no, it doesn't mean what megaparsec is, but what length is that you measure?
So that's a simulation box. Basically, we simulate very big volumes of the universe. Universe is roughly 14 gigaparsec, and this simulation is 1.5 gigaparsec, so it's a big chunk of the observable universe. But it's not resolved down to star forming regions, so it's a kind of big simulation with coarse resolution. But this y-axis is just a slice of simulation box size. Sorry if it wasn't clear.
And the TB, what does it mean when it's negative?
Sorry?
When the TB is negative, does that mean the 21 centimeter is absorbed?
Yes, exactly. So exactly when it's negative, it means we're in this regime when gas is colder than radiation, right? And so from this formula, we see that it's negative if gas temperature is this term is larger than 1, but in negative, right? And so you get absorption signal. So CMB photons go through hydrogen gas, and it's colder, so it absorbs faster than it emits. And so overall, you see negative signal, or we say it's seen in absorption.
Thanks.
One of your slides, you had 3 sort of scenarios at the top. One was dark matter annihilation.
Oh.
Is that a realistic thing?
It is, yeah, it's realistic. We still don't know what dark matter is, right? We know that it's composes roughly 80% of total matter, total gravitating matter. And that's basically it. We know that it's not very hot because it does collapse and form structure, but we don't know what particle physics nature of dark matter is. And experiments such as Large Hadron Collider in Geneva, right, CERN, they are trying to constrain these properties. So if you bump matter at very high speeds, part of its products would be dark matter particles, and then if it annihilates with itself. So it's when two dark matter particles collide, they can maybe annihilate in some parts of dark matter theory spectrum. So if that happens, the energy doesn't disappear, it is transformed, say, into other particles. It can create a particle shower composed of electrons, pions, other standard model particles. And if it happens, so if you say create a lot of electrons would affect the 21 centimeter signal because they contribute to the ionization and gas temperature factors. So in principle, there are many models that are not constrained by LHC, but can in principle create signals in 21 centimeter signal, create features in the 21 centimeter. So I don't go into details here, it's like the full other topic.
Question? I have another one. That's great. It's more of a curiosity. Could you give us a bit more details on the simulations? So what kind of software do you use? What kind of numerical methods?
I use MATLAB. So the simulations, so I wrote it as a PhD student in MATLAB because I started as an electrical engineering student, and that was the language I knew. So it's MATLAB is very good with matrix multiplication and manipulation. And this simulation, so you take basically initial conditions from cosmic microwave background fluctuations in matter density and velocities, and then evolve them with time. So from cosmology courses, if you've taken, you know how perturbations grow. So basically dark matter grows also in the simulation and forms dark matter halos. And then because these are very large cosmological simulations, so 1.5 gigaparsecs, even on modern computers, you cannot really resolve to very small scale. So you cannot really simulate in one simulation big volumes and star formation. So you need to compromise, and the compromise is that we have very coarse resolution. So every resolution element is 3 megaparsecs. But then one needs to kind of write in prescriptions, code in basically how universe looks like in every 3 megaparsec subregion. And so there is a prescription that is called halo abundance that gives you a number of halos, dark matter halos within every region. And you see variations here, right? So there is variation in the simulation on large scales, and it means that every 3 megaparsec region has different conditions. So some are in overdense regions, others are in underdense regions. And those in overdense regions will have more halos, have more stars forming early on. So there is a prescription for star formation, which we take from other simulations, so theoretical understanding. And then we can calculate how many stars are formed in every subregion. And then if you assign a spectrum to every star, you can calculate how many photons are produced in every frequency band. And then kind of, so photons fly with the speed of light, at what distances they will propagate. So you can kind of look back in time from every gas cloud and see how many photons are incoming from around. So kind of do light cone calculation. And there is another prescription for ionization and so on. So there are many things.
Yeah, lots of things to take into account.
Right.
Thanks.
Still on the same slide, you mentioned machine learning.
Oh yes, so machine learning we do all the way. So so this is a result of one simulation, and it runs 3-4 hours. So it's very fast compared to hydrodynamical simulations of galaxy formation, but it's still 3 hours. And to do what we call statistical inference, so to try to find, say, the value of star formation efficiency from one simulation, to fit simulations to data, build something like that. It takes millions of coins in the parameter space of astrophysical processes. So going from thousands of simulations that we can actually run to millions of the samples, we use machine learning just as a, kind of to interpolate. So we run simulations over the, but if you have a large astrophysical parameter space, so star formation efficiency can be between 0 and 1, right? And it cannot exceed 100%, but we do form stars, so it's above 0. So we kind of run simulations within very broad ranges, and coarsely sample this star formation properties. But then we use machine learning to kind of sample more finely. And this is pretty easy to do, I say, but my students do that. I didn't do that myself, so they do it easily. So we create this large kind of samples, and then train emulators, what is called, using neural networks. And then these are used in this Monte Carlo Markov chain analysis to fit each simulation, each parameter value to data.